So we're going to look at our work and our technical information and the cosmonauts and astronauts reports on the missions accomplished. I would like to recall that we have all undertaken missions in space, and it's always with a great deal of emotion that we remember our missions in space. And yesterday we spent we had some very moving presentations when we saw this magical star, the International Space Station, that crossed the sky just above Toulouse, and it reminded us of our missions on board the International Station. And of course, our schedule in space is always very, very busy, but the presentation of Boris Enko will also be very moving, I think. So I suggest that we listen to his report on his work within the framework of the 4950 exhibition. So Andrei, over to you.
Добрый день, уважаемые коллеги, дорогие мои космические братья и сестры, с кем мы вместе поработали на орбите, с некоторыми хоть чуть-чуть, но все равно поработали. Тема моего сообщения, как сказал Александр, посвящена результатам работы.
And just as Alexander explained, I'm going to talk to you about the results of the 4950 mission on our scientific program and what we achieved within the framework of that mission. Before sharing figures with you and the names of the different experiments, I would like to show you a short video on our preparatory work, the preparation of the members of our team. I'm sure that some of you, once you've seen the film, will remember your own preparation program. So I'm sure that everyone will find this very interesting.
деятельности в российском сегменте.
There was no work outside the space station during the mission, but we did carry out a lot of training.
Как и у всех остальных экипажей, в нашу подготовку были включены также тренировки в зимнем лесу.
And of course we had training, we trained in the forest during winter, so that all of the teams were trained to survive in water. Our team visited Baikonur twice during the preparation for the mission. The first time that we went back to the Star City and come back to Baikonur, and I'm going to explain why that happened later on.
Спасибо. Ну, конечно, экспедиция у нас была не такая короткая, как показано в этом видеофильме.
So, of course, our mission was not as short as you saw on the video, so it looks as if we just fly off and then land back on Earth, but that was not how it worked. I think that we spent 182 days on board the space station. It was just a very short moment in time. So here you can see the program for our mission, 4550. The program includes a number of specificities. First of all, because our transport vessel, MS2, was not technically ready to fly out to the International Space Station. Therefore, we delayed our flight. And first of all, it was the 19th of December. And so we delayed it, and it actually flew out on the 1st of December. Unfortunately, that was not the only hitch, and the 21st of December 2016, due to some technical issues, the vessel MS-04 could not be placed in Earth orbit. There was a breakdown during the flight, and then because the launch date of the next vessel was delayed until the 22nd of February 2017, we changed the dates of our departure. So we were very happy actually about that, because obviously the work in space, we were very happy to be working in space.
Состав экипажа.
So, sorry, bit of technical problem, missed the beginning of the sentence. So, explanations 49 and 50 for the other players already mentioned. And Robert Kimrow was the commander on board for our expedition. And we were very happy to work with him. So, these are the objectives that we achieved. 6 operations for docking and undocking. We also used the vehicle HTV-6, and then we had we docked with Hermes 05. The vehicle did not reach the station, and therefore we extended our expedition, and we also continued our work on the scientific program. We didn't receive supplies, including 2 types of very important supplies for our experiments, and this is why we were obliged to cancel 2 of our experiments. On the Russian segment, we were not able to carry out one of the experiments, and we were not able to check the system, the regeneration system for water retention, and that is something that we should have done in the Russian segment. During our expedition, we went out into space on 4 occasions. Although this was not, we had not planned to do this. And this was to carry out work on the American segment. Our team also helped our colleague when he went out into space with the scaphanders. And also during the different manipulations. During the work planned in the Russian segment, our colleagues on Earth processed the data and also calculated the time required to carry out the work in the Russian segment. Here you can see a pie chart on the slide, and you can see that we spent more time carrying out scientific tasks. Sergei Rychikov and myself spent an equivalent amount of time, a little more than 30% of our allocated time. If we look at all of the types of work carried out in the Russian segment, here we can see the work on the payload linked to equipment operations. And so you can see our figures, 40% of the time was spent working on the payload, and more than 50% was spent working on the ISS equipment. Not only the Russian segment, moreover, because we did spend a certain amount of time in the American segment. So these are the operations that required the most time. So this is at work with onboard systems, for example. The verification work on the ventilation systems. These are tasks that have required the most time so far. We also carried out a large number of experiments in the Russian segment, as I said, including a number of experiments in the field of physics and chemistry related to the study of the behavior of materials in space. The crystal experiment and Zaleva experiment. Zaleva was carried out in the American segment with our colleagues from the United States. Crystallizator was an experiment on the crystallization of macromolecules and the obtention of biocrystal surfaces. The crystal was a very lengthy experiment. I contributed to this already in 2011. The idea was to study the dynamics of loaded particles in a magnetic field in conditions of microgravitation. So, we studied the Earth and space in the experience du Bravo in order to study the ecosystems of forests. Relaxation experiments also. The idea was to study chemical systems within the environment from space. experiments in seismic sciences, where we had to process data that were forewarnings of earthquakes in order to give early warning for emergency situations and disasters. The Oregon hurricane experiment was also designed to foresee and to prevent from Earth-based surveillance stations situations of emergency and disaster. The largest group of experiments carried out in the Russian segment could be named Man in Space.
Это эксперименты альгометрия, исследование болевой чувствительности.
For example, the algometric study
очень интересный эксперимент и достаточно
was a study to test for sensitivity to Spain during space flights. The experiment BMIS studied the information system for medical care that were integrated in the onboard systems of the International Station. The BioCard experiment studied cardiac activity using a specific application and an ECG, an electrocardiogram. The Interaction 2 experiment was carried out thanks to our specialists in psychology, and this was to study the interaction between persons of different nationalities among the team, among the flight crew, and the interaction between persons and the interaction between groups of different nationalities. The experiments called DAN was to study microreceptors that monitored the respiratory systems of the people on board. I'm not sure whether it's worthwhile actually running through the content of all of the experiments, but I just would like to mention in particular one group of experiments which were related to technologies around space exploration. There aren't that many of them. There are 9 of them, 9 experiments, but they are highly important for future flights. The albedo experiment was to study the radiation from Earth and the its use for energy on the ISS. Then Barr studied the monitoring and identification of places where there was a loss of air tightness and water tightness in the ISS. And the last group, which required the greatest amount of time, were not actually experiments as such, but rather the dissemination of information, and therefore the interaction with users on Earth and students in schools and universities. So we also studied with exchanges with studies. And then there was a Gagarin program with regard to Gagarin, which is starting from Cosmos. And this was a radio emission from our international station. And also an international experience that experiment led in common with the Americans, which was the synchronized guidance and change in direction of the experimental satellites in space. So this is the time spent on the different experiments. Sergei did 313 hours and myself 296 hours just on carrying out these experiments. So that is the end of my presentation. Thank you very much for your attention.
Thank you very much, Andrei. I hope we can have a few minutes at the end of this session to answer a few questions. That our technology does have a future. Now, as the moderator of this session, I would like to say that the space exploration process, we are quite humble in our relationship with space. Issues are not done with, and we are not yet familiar with space. I'll remind you that 2 weeks ago, the 4th of October, we celebrated our 60th birthday since the launch of our first satellite. So I will use this to transition to a new presentation. We have prepared a short presentation to tell you the most important facts. There are lots of very interesting details, but I would not like to take too much of your time. So, with your permission, my presentation. The generation of individuals that made the switch to the 21st century witnessed the first steps of search exploration. Some very famous people, Sikorsky, Goddard in 1922, Aubert in 1923, others started arguing that this concept was feasible, but space flight only became possible after the large-scale development of celestial mechanics, rocket building, IT, communication, and all these new technologies calling on specific properties. The humankind was just developed enough to start exploring space at the middle of the 20th century. Some missiles created just after the Second World War were the starting base to start having space vehicles. In the US, we had a satellite that was built in 1952 for President Truman. Then Eisenhower, in 1955, made the decision to launch a scientific satellite. Declaration was prepared and approved by Congress on the 29th of July 1955, and then a communication was made by the secretaries, stating, on behalf of the President, I hereby declare that the President has approved the satellite of an unmanned satellite on a terrestrial orbit. This was part of the US contribution from the International Year for Space Exploration. This program will, for the first time, give the researchers worldwide the possibility to regularly observe the world from outside the atmosphere. On the 20th of May 1954, in Soviet Union, we adopted a resolution to develop an R-7 missile, two-stage. Some days later, 27th of May, Sergei Koglev made a report to the Defense Minister, Dmitry Ustinov, on the possibility to launch a satellite using the R-7 rocket. Decision to develop an artificial satellite was made in August 1955. At the end of 1956, the first launcher, the ballistic intercontinental missile R-7, was built and tested on launch site of the Defense Ministry in the semi-desertic zones of Kazakhstan. The first R-7 launcher was transported to the firing platform in 1957. The first launch failed in May. The second didn't take place due to a failure of the oxygen system. Then on the 12th of July, after a launch and a short flight, the rocket fell 7 kilometers away from the site due to a guidance system failure. 21st of August and 17th of September, the launches succeeded, but the equipment did not stand the high temperatures and disintegrated. 6 months were required to improve the top stage. Then Kovalov decided to prepare the launch of an elementary satellite during the 100th birthday of Tsiolkovsky. In September 1957, Sergei Korolev, in his presentation to the research scientists, said the USSR and the US will soon proceed to the first tests of artificial satellites for scientific purposes. The scientists involved in the construction of the rockets had time to build an elementary satellite and improve the R-7. This roadmap was also good for the research scientists because Science Academy was taking part in the geophysics year. This way they could receive and process information from the satellite they launched. A non-specialist was finalizing the rocket based on an intercontinental missile. The R-7 had the following modifications. The guidance elements were modified. The top-part adapter was replaced by a casing holding the satellite, and also they modified some of the systems. The weight of the rocket was reduced by 7 tons. The R7 rocket was taken to the launch pad. You see it here. And Friday, 4th of October at 10:20 p.m. launch succeeded and placed the first ever artificial satellite on orbit. The center stage, weighing 7.5 tons, and the elementary satellite, weighing 83.6 kilos, were placed on orbit. The orbit was 87 kilometers in apogea, and perigea was 227. 314 seconds after it separated from the second stage, the satellite started to send radio signals using its transmitters in the 20.005 and 40.002 megahertz. Some data on the satellite condition was there. The transmitters worked for 2 weeks before the battery ran out of power. 14 days later, after 1,400 revolutions around the Earth, the elementary satellite went to the atmosphere and ceased to exist. This orbit made it possible to assess the atmosphere density, which was quite high, 10 atoms per square centimeters, and this surprised the scientists. Density measurements for the upper layers of the atmosphere were used to study the braking theory for satellites to improve the longevity of the space equipment on terrestrial orbit. The way the radio frequencies penetrated the ionosphere was studied, and this had only been studied by electromagnetic waves emitted by terrestrial stations. But the most important is that we have confirmed the possibility to place payloads on orbit, terrestrial orbit, and thus contributed to the future technology for interplanetary flights. The value of this payload cannot be overestimated. For weather purposes, climate study, for instance, the volume of data obtained daily by our satellites is £1.5 million. The automatic observatories of the interplanetary stations we have launched during the 60 past years made it possible to improve science and discover the mysteries and miracles of the Earth. Artificial satellites paved the way for new possibilities to develop automatic systems worldwide. And if the geopolitical climate is favorable in the 21st century, the first spaceship holding humans will certainly reach Mars rather soon, and it's quite possible that one of the participants of this mission will say, "Space is my future." Thank you for your attention, and we will continue with our Congress. Thank you. Now, back to present days. We discussed history, and I would like to give the stage to the next presenter. He is going to tell us what are our plans for the future, what we are doing presently. He will tell us our projects to develop information systems and research technologies using existing equipment on the International Space Station, and this ISS will be the base we will use to increase our presence in space. Yuri Gitsenko, I cannot see him. Please come and join us on stage. Today he will tell us what the plans are for the future. I think he will show you quite a lot of pictures to illustrate his theory. Well, it's not, well, as far as he's concerned, it's not a theory. So, good morning, dear colleagues. As Alexander already told you about the event we commemorated recently, the 60th birthday of the first artificial satellite, I would like to add that yesterday we celebrated another event, the Progress spaceship docked on the International Space Station to deliver equipment, food, spares for the ISS systems. This spacecraft should have taken off the 12th of October, and for the first time we wanted to use the short docking system after 2 revolutions around the Earth. 3 hours after being launched, the spaceship should have docked to the station, but unfortunately we could not do this on the 12th of October. We postponed the flight a few seconds before launch, and the launch date was pushed back to the 14th of October, and it took 2 days to dock. So my astronaut colleagues, Andrei and Catherine, told you this and gave you all the details about the work and the experiments we do in space when we are in the International Space Station. I will myself give you a few more details, tell you a bit more about history, and tell you a little bit more about our future too.
Вопрос в чем заключается? Нам надо понимать, для чего мы вообще летаем в космос.
So what is the problem? We have to understand. Why do we go to space? Why do we study space? Of course, it's useful to improve life on Earth. This is easy to understand. Improving our communication means television, Internet, us experimenting in space makes it possible to improve the quality of life on Earth. But in the future, we want to go even further, leave the Earth orbit, go all the way to the moon. We even have satellites launched 40 to 50 years ago that already went beyond the solar system. And of course, this brings new information, new knowledge, and that is always useful. These men were at the very start of the space flight you see Sergei Korolev. 60 years ago, him and his colleagues worked together to build rockets, to build also new equipment launched from the earth, launched from the sea. They all worked with these systems. These are our famous countrymen. So we have 4 Academy members: Sergei Korolev, Igor Kurchatov, Mstislav Keldysh, and Vasily Mishin. And I'll read what Mr. Korolev said. Manned flying in space is essential for research because such powerful automatic equipment, such perfect equipment will never replace man in space. This is what Korolev stated. On this slide, you see a diagram. This is the start of the human flights until today. I can split it in several stages. First, you have the accumulation of knowledge, of information, accumulation of experience after the first flights. These are the Vostok and Soyuz spaceships, the first spaceships. Then we had the improvement of technologies to improve our knowledge. These are long-term missions. The Salyut vehicles, these were small, but nevertheless they made it possible to experiment, to study the behaviors during long-term missions, and quite logically the result is what we had in 1986 with the launch of the Mir space station, which is the ancestor of the International Space Station. We don't always realize this, but in a year, in December, we shall celebrate the 20th birthday of ISS, and this was launched 20 years ago. Here you see the history of manned stations. You have the Soviet Salyut missions, Salyut 1, 3, 4, 5, 6, and 7. We have Mir and the ISS. They've been here for over 18 years. And they have been manned for 17 years, and you also see the Chinese stations. One of them does not exist anymore, and another one has been in space for a year. These are photographs from our Salyut stations. Salyut 1, 3, 4. They were quite simple. They were not as sophisticated as Salyut 6 and Salyut 7. These two, Salyut 6 and 7, made it possible to test all the technologies we needed to dock the Progress spaceships, and this knowledge was extremely useful for our later work with the Mir station and the ISS. You know that the space station can go down 30 meters per day, so its position has to be corrected at least every year. This means that there is always a possibility of impact by space debris, meaning we also have procedures to recycle these debris. This is the Mir space station. I was lucky enough to work in Mir. We proceeded to the second docking between the shuttle and Mir. You see the red part is the STS-74 module, and this was brought to us by the shuttle. Chris Kettle piloted this module to dock it on Mir. It's 135 tons. I will now show you the ISS to give you an idea of all this. Why was Mir so unique? Trikolov and May worked on this station, but the first expedition were manned by Kizim and Solovyov. In fact, they left one station, then went to another station, and then went back to their first station. So they went to Mir, worked a while on this, and then they went to the Soyuz station, worked there, removed some pieces of equipment, and then they went back to the Mir station. So they visited two stations during one same mission, and no one had done that before. Now, the International Space Station, Mir weighed 135 tons. ISS is over 400 tons now, 434 to be precise. Depending on what spaceships are docked, so the weight can change. It's over 1,000 cubic meters in volume. It can host up to 6 people. It is planned to operate until 2024, but this lifespan could be extended to have an idea of its dimensions. For those who know Moscow, you will understand what you see here. It's the Red Square with the Vasily Cathedral, historical museum, right and left, and the ISS in the center. Systems become more and more complex, the stations become more and more complex, meaning we have to spend more and more time planning the mission programs and the flight programs. You can see on this table here the first missions, the first spacecraft, the number of operations. Very few of them initially, and we didn't have a lot of data to send to Earth. If you look at the data sent by the ISS, there are tens of thousands of parameters. They have all sorts of configuration options, and the volume of data we can transmit to Earth, you can see it on the right column, was in excess of 120,000. These are huge volumes in Moscow, Houston, Toulouse. We have specialists monitoring permanently the data flows and analyzing them. It's impossible for a man to process all this information. We have specialized software with mathematical applications to make the most of this data. Once in a while, we ask the question, should we continue with our manned flights program? It is not always as efficient as we would like, but the presence of man in space, man and not a machine, is essential. Cosmonauts, astronauts will always find a solution. They can, well, with the help of the ground stations, he can repair some equipment or adjust them. And of course, it is thanks to the manned flights that we can improve our flight techniques, our station configuration, to improve the efficiency of our work in space. Why do we need the ISS? Well, first, it is a laboratory, and this absence of gravity is impossible to simulate on Earth, even using zero-G airplanes. It improves our knowledge in physics and biology. We understand what happens under vacuum. The study of biological structures. All these are possible with microgravity. The diagram you can see here shows you some percentages of the experimentation we do aboard the ISS. You can see here that we have human in space, physics and chemistry, technology, biological technology, and our colleague Tokoi said everything about education. It's key for us to inform our youth, our children, raise their awareness on our activities to give them a future taste of space. Andrei already told you about what you can see on this slide. For astronauts, cosmonauts working with the payload, meaning experimenting with the equipment, takes roughly 50% of their time. That means 15 to 16 hours per week. Of course, there are some exceptions. The 2nd of September, Fedor Yoshikin with Peter and Peggy Wilson came back to Earth. Fedor was alone in the Russian segment for 2 months. He had a huge workload to maintain the station, meaning he was not doing a lot of research and had only 15% of his time to give to research. But this is an exception. Here you see photographs of various experiments, information on the number of hours spent experimenting from 2000 to 2016. When I went to space with Sergei Trikolov and Sergei, we worked in the station, worked on cables, worked on equipment, and it took hours and hours. We had little time for research. We still did a few experiments with crystals, but they were exceptions. The station now has become a real international laboratory. We do lots of very important and high-quality experimentation there. Here you can see the 6 major categories of our expectations, what we want to obtain with our experiments in the various fields of science. Now, a few words for our future. What is in the plan? If we adopt a strategic view, it will be a manned flight to Mars. But this is mid or long term, because technically it is rather difficult. First, we have to think about flights to the moon. And to fly to the moon, we have to consider the future of the ISS and what will happen next. We want to create a Russian space station based on the Russian segment of the ISS. We are designing a new spaceship to go to the ISS and to other future stations. And of course, we have in mind the manned flight to the moon. This is how we see the future of the Russian segment of the ISS. The American segment is nearly completed, but we are planning on another research module to increase our research capabilities on board the station, and also an energy module. Here they are. This is the scientific module, as we call it. And this is the power module. You know that we often lack energy in the Russian segment. The Americans supply the energy we need quite often, and this module will increase the available electricity. This is the Federation spaceship. Launch is planned for 2021, and the first manned launch is planned for 2023. For what concerned the Russian station, initially, this is what it will look like. This is the science module. This is the docking module and the energy module. They will be released from the ISS and will join the new station. As I said, we have to go to the moon, meaning we will need heavy rockets. If we wanted to reach the moon, we need the capacity to send over 200 tons, 100 tons in orbit for the moon and 200 tons for Mars. I know our American colleagues will test their rocket next year. And a few more words on the moon platform. This is one step. We want to create a base camp on the moon so people can spend a while on the moon. And then we can imagine further flights to Mars. And I will cite some words from Keldysh, our academician. We are in living days now where we have to conquer the mysteries of nature and space and the new phenomena we are going to discover on other planets will be used to improve life on Earth. Life doesn't stop, it continues, and I hope we are going to do lots more of interesting things on the ISS thanks to our international collaboration. Thank you, Yuri. This was a very nice flashback. Dear friends, we are running out of time. We have finished our